All right, welcome to a lecture on a very magical topic. It's called virtual memory. It is like the backbone of major operating systems. It is the reason that we can run multiple programs at once and not run into trouble. It's the greatest thing ever, and it's time we learned about it. All right, we're going to learn the secrets. So there is a bit of your textbook about this, so please go into your Dive into Systems textbook and read chapter 13. Though you can just focus on the virtual memory part of it. You can skim the rest. But definitely read about virtual memory because it's so cool and it's so useful. All right. So here's the idea. Here's what virtual memory is all about. So back in the day, the dark ages, when like it was rare to have a computer at your home and like microprocessors were brand new. Most computers were like at people's workplaces and they took up an entire room. Back then, something called memory protection wasn't around. And memory protection kind of sounds nice, right? Back then, without memory protection, every time you went to an address in memory, in your program, you like dereferenced a pointer or something, that address, it mapped directly to your stick of RAM. If you went to address 74FB or something, then you dereferenced a pointer that held that address, you legitimately went that many bytes offset from the start of your stick of RAM, and you went to that memory cell there, and it gave you the byte value back, or whatever contiguous thing you asked for, okay? That's without memory protection. That kind of sounds normal, right? Because we've been tricking you so far in your computer science career. It's time to not trick you anymore about this. So a physical address, again, it's just like the actual number for a cell in physical RAM, your stick of RAM. Like you go to this address, it's that much offset from the start of your stick of RAM, all right? We've been assuming that, like, yes, if I go to this address, that's where it's going in memory. That's what I thought this whole time. But no, that's actually not true, all right? Think about it, because if you knew the address of like a place in one of your programs, then you could make another program that goes to that address, and now it's suddenly reading your other program's memory and like getting access to passwords and things. That's not okay. All right, so we would like to protect our memory. We'd like to use virtual memory. Pretty much every program these days uses virtual memory, other than the operating system itself, because it has to manage it for us. All of the programs that we've ever written are using virtual memory, which means if we go to this address, it may not even be in RAM, first of all, and then if it is, it's definitely not in this address. And in RAM, this is just a secret address that's being translated into something else. All right, very, very unlikely it's the same place. So here's the secret to virtual memory. Every process, every program that you have running thinks that it's isolated. It, first of all, pretends that it owns every memory address, which is, impossible. Because like there's not enough, like with 64 bits of address space, because that's how much you can put into a pointer in our ARM machines, you get like over like multiple petabytes of memory that's accessible, even more than that. I forget the actual prefix, but like you can't buy that much RAM right now and stick it anywhere. So like there's so many addresses that you just can't go to, but your process thinks all of them belong to it. It has that much space, all right? Maybe more than is even installed on your computer. And it also thinks that it's isolated in the sense that it's the only process that's running. Nobody else owns any other memory addresses. That's kind of interesting to think about. So like here is what your process thinks it looks like, all right? It's virtual memory though. Your process thinks that it was loaded starting at address 0000, that one, the smallest address. Like here's what memory looks like to your process, what it thinks it looks like at least, right? And like here's address FFFF, all that. It thinks all of that belongs to your program, all right? But it's only using pieces of it, like this part is the data section, this part is the stack or whatever. Different sections are things that are actually being used, but if this is virtual memory, here's actual physical memory. Let's say you try to go to an address that is somewhere within this chunk. Actually, what's happening is that address is really being stored somewhere at the start of your stick of RAM. Secretly somewhere else, all right? Though it is in physical memory, it's just at a different address, all right? It doesn't know which one. It's just, all right, I go to this address, I'm getting the thing, but really, in physical memory, it lives here. Same with this chunk. You store a few things in this chunk of RAM. Those are being mapped to maybe this place in your physical memory, in your actual hardware of your computer, okay? It's a different spot than where it really thinks. It's not the same address these days, all right? It's not even as much, right? Not even as much address space. So hopefully you don't try to use it all because you'll run out of memory. But like in real memory, right, in physical memory, you got operating system specific stuff loaded in, which you can't see, you're not allowed to see. You have other processes running on your machine that have their own memory addressed to them, and you don't get to see those either. So like maybe this weird address way up here like maps to like offset address 42 or something. Who knows? You don't get to know. And then even like maybe this chunk, you try to go here somewhere, or here, like those are pieces that you can't even fit in physical memory, it's so big, then those are really saved on disk if you try to go to them. We're going to have to read them off the disk back into RAM real quick, because like we don't have enough room for that right now. And that's like an illusion. That's what virtual memory does for you. It just like it provides the illusion that you have so much room, when in reality the operating system is managing like where it really is for you. Okay? So that is virtual memory in a nutshell. It is wild. It's super magical. All right? It's pretty cool. All right? So well, let's talk about this. It's like a lookup table, essentially. This is not the real address. Your program thinks this is a real address, but no, it's being mapped somewhere else. Let's talk about that mapping, right? So one neat fact, right, is if you run 2 copies of the same program at the same time with the same input, and you turn off something special that exists in Linux, don't worry about it, then if you were to do that, then their virtual memory use looks exactly the same. You run P1 and P2, 2 copies of the same program, and you give it the same exact input, then it's going to store everything in the same place. Process 1, which is living in memory right now, thinks that if you go to address 1234, that's where the X variable lives. If process 2 tries to access variable X, it also thinks it lives at address 1234. They both are storing something at that same address, but as we know, that address isn't actually a place in RAM. It's being like mapped somewhere else, wherever your program got loaded. So that's the secret, all right? Their address space looks exactly the same. To each process, the same variable looks like it's in the same address, but it is not, because that would cause problems for us, of course, right? So that's the idea. Here is it's like they're both living here in the stack, the same place, right? They both think that they take up all the addresses. Like this is the lowest address space, this is the highest address space, that's where your stack starts always. But of course they'd clobber each other if that were really true. They both think that memory looks like this to them. But no, it's just being remapped, okay? So they're really, both of these things, their virtual memory looks exactly the same, but in reality they were loaded into different physical locations in RAM, if there was room, all right? So here's like P1's, this is the memory it's really getting in your physical RAM. It's getting these addresses, and so its X is really living right here or something. It's like, I don't know, address 21234, all right? That's the idea. Whereas maybe P2 got loaded here, and its X memory address was like 41234, right? It's really an offset, essentially. You can think of it that way. Like, its 1234 was really 21234, or 41234, whatever, okay? So they're getting their own version of X, they're getting their own space, and they're being stored at different physical addresses, all right? And that's, physical address is the concrete place in your stick of RAM, all right? And then also, all that OS code that they think belonged to just them, like that would be a waste of time to duplicate that across all the processes, because they all want the same code, and so like that's being loaded once and like everybody shares that place. You go to some small address, it's really getting you OS code anywhere. It's not being duplicated all over your RAM, okay? So isn't that weird? That's odd to think about, but that's the truth. That's the fact of the matter. You have been lied to up until now. I'm so sorry, but like it was for your own good, and now you're ready to know better. So many advantages come with virtual memory. That's why we have it. So first thing, very important thing, no process can like, oh, I'm just going to go to address 1234 and then I'm messing with somebody else's memory. Like they're all racing over the same spot. That's not good. All right, they can't clobber each other's stuff, which is nice. Also, because like you don't have to put everything in your physical memory at once, you can save some things for later that are not frequently used on your disk. Then the same program, it can run on a computer with a tiny amount of RAM and another with a lot of RAM. Like you don't have to like figure out like I need to make sure that I've reserved these exact addresses, and if I don't have the RAM for it, like I can't run my program. That's not true anymore with virtual memory. All right, and so there's a concept of a virtual address space. That's the addresses that your program thinks it has under virtual memory. It's just all one big mirage. It gives the illusion that your computer has a bunch of memory, exabytes of memory, but it really doesn't. All right. And the operating system can like swap things in and out and make sure it seems as if that is true, all right? So, yeah, the operating system tries really hard to not run out of memory when it can, all right? Even if there isn't enough room in RAM for every currently running program, it will save some things. It'll like put them in the freezer, which is your disk, all right, and get them back when you need it. So that's really cool. All right, it's really, really cool. Okay, so here is a question for you. Go on the server and run this command. It's called htop. Here, I'll do it. You try. All right, it's a command that lets you see the current running processes. htop, and it's always up to date. So like here's the state of our machine. We got 4 cores. Here's how much memory is being used, etc., etc. But all these programs, each of these lines are different programs that are running, and they're all taking up memory. All right. So there's a virt column. That's how much virtual memory that the process thinks it has right now. All right. And if you add it up, you'll notice that it's way more than we have. We have 8 gigs of RAM, but like this program right here thinks it has 8 kilobytes of memory. This program right here thinks it has 107 megabytes. This other program also thinks it has 107 megabytes. These like 5 programs together think they all have like 2 gigs of RAM apiece, when in reality we only have 8 gigs of RAM in our machine. That would already like be running us out of memory, wouldn't it? And the reality is they're playing nicely still. They're not using all that amount that they think they have. Okay, so yeah, there's also a res column. All right, this is virtual memory use. This is how much it thinks it has in virtual memory. But res stands for like residential. I forget. That's how much memory is actually being used by the program. So even though this program thinks it owns 2 gigs of RAM, it wants that, but it's actually only used really 55 kilobytes of RAM. These are byte values without a suffix. So yeah, that's pretty nice. Okay, so with the illusion of space, you can do cool things. And can you find the process on this computer on our class server with the largest difference between virtual memory and physical memory? It honestly might have been the one I'm just talking about right now. You can sort by. There's an F6. You can do F6 sort by mvirt. All right, and yeah, I'm pretty sure it's going to be one of these guys. Crazy. And these are actually a bunch of processes that run that are part of the autograder. The autograder is hooking into this. So that's kind of cool. But I like to keep it sorted by CPU time so I can see who's using a very, very fancy command that's taking up all the CPU power of the machine. So yeah, that's virtual memory versus actual physical memory use. So it can tell, your process can tell, the operating system can tell you how much. So yeah, that's the goal. It's like you go to this weird address, you go to some address that you think lives here, but it's really being remapped to some other place that may not even be on your stick of RAM. All right. So the goal is every time you go to an address in your program, like I go to address 1234, then it's the job of somebody to tell me like, oh no, really, like you're reading this value, like the CPU is doing a load instruction, you're really actually going to go to this place in RAM, CPU. And the person whose job that is a piece of hardware called the MMU, all right? So we want to translate from virtual addresses to physical addresses, all right? That's my silly joke of the day. So yeah, the processor, like every time, like every program except for the operating system is using virtual addresses. So you need to be very quick about this mapping of like, okay, you go to address 1234, really you're going to address 21234 or 41234. You have to figure out which one really fast so that there's no speed taken away from your program, all right? So where was I here? The MMU is the place that this happens, all right? It needs to be very quick at translating virtual addresses that your program thinks belongs to it, to physical addresses, actual places in RAM, wherever it really was placed, okay? So we actually have made hardware to do that for us because we want to do it very fast, all right? So the piece of hardware is the MMU, which is short for the Memory Management Unit, and that is where there's like a big mapping table that like the CPU goes and it's like, hey, I am this program, I would like to read, please give me a load instruction, read from this address. You feed that to the MMU as you're actually trying to talk to RAM, and the MMU spits out, oh yeah, go to address 104, that's where that thing really is. And so that's where the load instruction is really going to load from, but your program is none the wiser. It is like sectioned off. It doesn't get to know what the real physical address is. But when you look it up, it's going there, okay? the operating system is keeping track of the mappings and like putting it into the MMU for your current program, right? So that's that. That's where it happens. We'll have some more examples of that in a second. But there's one last secret, all right? Because just imagine you're trying to make a mapping. The naive way would run you out of memory real quick, all right? So like in the MMU, you'd have to save stuff for your entire program. Like, okay, yeah, address 0, that maps to 1, 2, 3, 4. Address 1, that's going to map to 1, 2, 5, 8. You'd have to store for each address where it's really living. And let me write this a little bit cleaner so you get the gist of the idea. 1, 2, 5, 8, I guess. And then this one is like 2 goes to address 1, 3, 8, 7. Do you see if you did it this way, like you would, for just one program, you would be using up more space than you have in RAM to just save the mapping of every address, right? So that's disgusting. Mappings would take up way too much space if they happened at the level of each byte address. And so in reality, we're gonna chunk up our addresses, and so that we never get into trouble like this. So like here are virtual addresses that your program wants to go to. Like here's what your program thinks memory looks like. It's virtual address space. Instead of like mapping each byte all at once to a different byte in physical memory, you're going to take chunks. You're going to take like this chunk, and you're going to map it to a physical address all at once. It's going to be a contiguous chunk, physical address. So here's your actual stick of RAM. It's really going to place all that stuff like, I don't know, it's all going to go like right here or something. And that's what's going to happen. All right, so this is called paging. So this is our trade-off that we make. We're instead not going to like save at the granularity of each individual address where it maps to in physical address space. We are going to chunk off our virtual addresses into larger pieces called pages. So like this is a page worth of memory, we say. It's usually like 4 kilobytes of memory. That's a page these days. And each page is going to be mapped to a corresponding contiguous chunk of physical memory. And to differentiate it and make sure that we know it's on physical memory, we're going to call it a frame. It'll be the same length. It's still 4 kilobytes or so. But every virtual page will be mapped to a physical frame. All right, that is the takeaway of this slide. Every virtual page, it's just a chunk of virtual memory, is really getting mapped to a physical frame. And that's the idea. So all of your virtual pages are being mapped to physical frames, we say. All right, and then you only have to store at the granularity of every 4 kilobyte chunks, like where does it live, and that makes the mapping much smaller. Okay, everything else is contiguous, and so that's an important thing to notice, and that actually teaches us something very cool and interesting. Actually, the smallest amount of memory. If you said like, I would like a new char, please, and you've never used the heap yet. You're like, new char, give me 1 byte of memory, please. And if you haven't used the heap yet, you have just allocated not 1 byte of memory, but 4 kilobytes of memory. Because if this is how memory works, every single allocation, if you haven't done anything yet, you don't have any places to reuse, it happens in 4 kilobyte chunks. Because you need, like, all right, you start using, if you just want this address, I need something here, then you need to put it in memory somewhere, in physical memory somewhere. And so there needs to be space for it. And if we're working at the granularity of pages, we must be using 4 kilobytes at once. So if you haven't used the heap yet and you make the first thing, you've actually just allocated 4 kilobytes of memory. All your everything you say next, if you allocate another byte, for example, is going to use that 4 kilobytes some more. But like the very first time, you have just used more than you thought, which is interesting to think about. All right, so that's called paging. The process of doing this translation and the mapping is called paging. All right, so here's a picture of that. So for example, here are 2 programs. This is P1, process P2 running at once. And instead of like asking about individual addresses, we're going to split up the virtual address space of our programs, of our processes, into pages. This is page 0. This is page 500. So like this is like the 500 times 4 kilobyte place offset. All right, so you're like offsetting by 4 kilobytes each time. That's frame 500, and it's 4 kilobytes. That's how we're mapping things. So these are pages, all right, 4 kilobyte chunks, and they're being mapped, right? If you go to this page somewhere, it's being mapped to maybe this physical place in RAM, which is called a frame. It's still 4 kilobytes, same chunk, but that's where it's really living. All right, so that's the idea. So for example, let's have an example. Let's say that process P1 wants to do a load instruction. It asks to read for address, it wants to go to address 500 times 4096 plus 2. And the reason I'm doing this kind of math is because 4 kilobytes is this many bytes, 4096 bytes. So that means this real address is page 500, right? It's page 500. I want the address at page 500 offsetted by 2 bytes, right? So that's within page 500 still, offset. Okay, that's the idea. Page 500, offset 2. So that's the address I'm trying to go to, all right? And then what the operating system is going to do, or the MMU is going to do, however you think about it, the operating system, eventually, somebody, MMU together, they work together, right? MMU, they're going to goes to frame, you can think of it one way or another, goes to frame, really it's being mapped to frame 513. Frame 513, and it notices that and gives you back, then the CPU is going to go and give you back the value at physical address. What was it? Well, it's going to be 513 times 4096 plus 2. All right. So now it's at frame 513, but it's the same offset into that frame. All right. Everything else is stored contiguously. That's the goal. All right. So you can store a bunch of stuff in your little 4 kilobyte chunks of each page, and those are going to map to different places. Like that'll map all to down here. All right. These guys, page 1000 will map to frame 100. Why not? For process 1 at least. And then like everybody else plays nicely. So like page 230 of process 2, you're storing all these things. It's really being mapped to frame 102. It's really, really close to process 1's memory, but we don't actually get to ever know that or have access to it. Isn't that nice? That's very powerful, okay? And like all these guys at frame 1000 page 1000 of process 2, it's really being mapped to frame 880. Like you go there, that's where you see that 4 kilobyte chunk of information, okay? So let's have some more pictures because we're not done yet, all right? So you have each address in your machine that you could possibly ask for, at least in terms of virtual memory, is the size of your registers. All right, so if you have a 64-bit machine, you have 64-bit addresses. And so if you have an n-bit machine, you have n-bit addresses, and we call that an address space of a certain size, right? How many addresses can you use if you have n bits to represent each address? 2 to the n, right? 2 to the n bytes worth of address space, we say. And that's virtual memory. Maybe you don't have that much RAM in your computer, okay? So if your virtual address space looked like this, with n bits total, bit 0 through bit n minus 1, you can use all these ones and zeros to make a virtual address. But maybe in RAM you don't have that much space, okay? Maybe in RAM you don't have that much space. Maybe you only have like 2 to the m bytes of space. And so the offsets into RAM would be something that's an m-bit number, which is potentially smaller, right? Does that make sense? That's what's going on here. And so it just so happens that 4 kilobytes is a nice power of 2, and so you don't actually have to like figure out, it's very quick to do this translation, because once you look up in the table, you know which page goes to which other page. It's really just replacing some higher order bits, and that takes you to where you need to go, okay? So say you have a page and it's like 4 kilobytes long or something. It's going to take up a certain number of bytes, and that means that like the offset into the page is like you can only use this many bits to offset into your page, and everything else we'll just use and call that our page number. That's kind of the idea. Like this would be an offset within the page. That's how many things you could like addresses 0 through 4095 or whatever, and then everything left over becomes your page number. All right, you can just section off your addresses just like that. And our goal is to like map each page to a physical frame, which is maybe a smaller thing. We don't have as much space, so we'll have to like spill some things over into the disk or something, but like we're going to map pages to frames, and the offsets will be the same. They will remain the same, and that's kind of what's going on. Okay, so here's like a concrete example. Let's say that we've got a page size that is 8 bytes, all right, because it's splitting it up like this, because your byte offset is 3 bits, which means your page size is how many things can you represent with 3 bits? It's 0 through 7, so 8 things, so it's 8 bytes, all right? Offsets 0 through 7, so page size must be 8 bytes. And your virtual address space is 16 bits wide, so you're going to use 8 bytes to figure out which part of the page you're in, like offset 0 through offset 7, and then everything else becomes your page number. Okay, that's the idea. So the rest, the 13 remaining bits, are your page number, and apparently that's like page 5419, and this is offset 5 into that. Okay, and then our goal is to map this, like we've saved a mapping from virtual pages to physical frames, like apparently that's going to go to frame 43, and we only have 14 bits of space in our RAM. So we're still going to use an offset, right? This will be our offset into our frame, but the rest, which is not the same, it's not 13 anymore, no, it's just 11 bits, that'll be our frame number. Okay, so it's our job is to convert these bits into these bits. That's what the MMU does really fast. All right, the offset remains the same. Okay, offset 5 still. So that's what's going on. That's what happens when we use paging. Let's see here. Dun, dun, dun. I think that is what I wanted to say about that. Okay, so yeah, the way that you store a mapping is it's like a hash table. We call it a page table. Okay, so it's going to store that mapping. You just go to an offset, and it's going to tell you where the thing should be. So the virtual page to physical frame mappings, they're stored in something called a page table. Each process gets their own page table because they have their own little mappings, right? P1 versus P2, they have their own mappings to different places. Yeah, remember that? So everybody gets their own page table, and that's stored in memory somewhere as well. Okay, so if you try to go to an address, like you try to go to address 500 or page 500, whatever, in P1 you have to first consult the page table, and that'll take you like okay, go to this one, go to this place in physical memory. All right, so we're taking up some space here. We got a space for P1, space for P2's page tables. So we're trading memory for virtual addresses, which is a great trade. It's honestly a good trade to make, because now we can't clobber each other's memory. We don't even know. P1 has no clue where P2's things are, and it can't even access them. The operating system will make sure, even if you try to go to somewhere like this physical address or a virtual address, one, it'll never map to the same place as P2's places, or two, if you try, like you'll either run out of memory or get a sig fault. Okay, it's great. It's just a wonderful thing to have. And so like here is the full picture. Now you have like a load instruction coming up or a store instruction coming up, which means you need to go to an actual address, all right? An address that your program thinks it has, which is a virtual one. So your program's like, all right, I would like to go to this address, please, and it knows that it's a virtual address, and so somewhere in actual physical memory, but not there, is where we need to go and look up. All right, so we're given this address, we're giving it to the CPU, and we're saying, okay, we're splitting it up right into a page number and an offset into that page number versus page offset. And all right, the job of the CPU now is it's going to, and the operating system is like, we've got to make sure that we have a page table in place. We have to know where it lives. We have to know where our current process's page table is, because now here's this address. Go to this page number in the page table, like apparently it knows where it is. It'll go to it. It'll go to this address. This is page number P. It'll go to page P offset in the page table. And it's like, okay, yes, it maps to frame F, and it's valid. It's actually in the in memory right now. It's not like saved on the hard disk or anything. So it's like it's got to get the F out, and then it does the translation. The MMU does the translation there to a frame number. So every page number is going to get mapped to that frame number. P became F, right? And the offset is along for the right. Like this was at offset D into the page, and so we're going to go to that same offset D into the frame because they're the same size, right? That's the correspondence there. And so I hope that makes a little bit of sense. We're also going to store some metadata, like is this frame valid right now? Can we actually do this remapping, and will it work? If it's not valid right now, we call that a page fault, which means like, oh no, it's on the disk or something. We need to load it in before we do anything, okay? And that actually leads to an idea called swapping, all right? If you go back to the class server, you do the H topic, and you'll see that there's some swap space that we luckily haven't needed to use yet. Actually, our server doesn't have any, but most computers do, okay? It's called swapping, swap space. And this is the same idea. It's this idea of like saving some things on the disk because we don't have enough RAM for everything, okay? So let's talk about that. The technical term is called swapping now. And so yeah, because RAM is fixed size, we only have so much. We can't it's hard to buy more. The operating system has to figure out like, all right, all these processes, they're fighting over RAM. Like how much do I give to each process? Which processors should have which pieces loaded in RAM at once? Because like each process sees like a giant amount of virtual address space, but there's only a smaller amount of physical address space. And so like the operating system needs to figure out like, okay, if I'm gonna deal with this address, then maybe I'll put that in this place in physical memory, but oh no, I don't have enough room for everything. Okay, so some things have to remain unloaded and just like swapped back in. That's where swapping comes from. So where do you put all the stuff that's unloaded? You put it on the hard disk, all right? Because there's a lot of space there. Remember the storage / memory hierarchy. Like your secondary memory, your hard drives and solid state drives are way down here. They're slow to access, but they hold so much, right? Much more than we have RAM installed in our computer. So that's what happens. We're going to put unloaded things on the hard disk. There's a lot of space, but it's super slow, so hopefully we won't have to access those things too much. Or we'll swap them into RAM when somebody does, all right? When somebody asks for that address. So we're going to take advantage of this spot, all right? So this is why it's called swapping. Your pages, if they are not in physical memory right now, they're going to be swapped by the operating system to the disk, all right? If there's not enough room to actually put them in a physical frame somewhere, all right? And so essentially you get to learn this. We've come full circle, right? So RAM has been a cache. Our main memory is a cache for our hard drive. That is a true statement, isn't it? Because like everything's getting loaded in when it runs, and it's being swapped out as necessary. It's been a cache for the disk this whole darn time, and now it's all unraveling. Isn't that cool? So yeah, that's the idea. And just like I was saying here, if something that you need was saved on the disk, like you try to look it up, it was an invalid mapping right now because it's saved on the disk, that is going to lead to what's called a page fault, which makes the processor stall for a second, and it needs to copy it in, it needs to find a page and swap somebody else out, and it needs to find a frame to swap out and like put it actually in physical memory when you need it, okay? So that's what page faulting means, and so you'd like your programs to page fault as little as possible, to swap as little as possible, because that's going to be talking to the disk, and we know that that is slow, okay? So with that, here's like a little exercise that's going to help you get some practice with this virtual address to physical address translation process, all right? So let's do this together. Try to pause the video when I think about something and see if your action corresponds to my action. But I'll do the first few. So using this page table, here's the page table for process 1. Here's the page table for process 2. It's like, this is the entry number, so it's like which page number it is. This is the valid bit. Is this a valid page to be read? And then here's the frame number that it corresponds to, all right? So we're going to assume that we have 8-byte pages, all right? 8-byte pages, which means, we'll figure that out in a second. Also, our virtual addresses are 7 bits wide, so here are a bunch of virtual addresses that we'd like to read from, and our physical addresses are only 6 bits wide. So our goal is to like take this virtual address, we're trying to read it, and to map it to a physical address. And it's only going to be 1, 2, 3, 4, 5, 6 bits wide. Okay, that's our goal. That's what's happening here. And all right, if we are assuming that we have 8-byte pages, where does that mean our page numbers versus page offsets live? All right. So like say we want to go to like our smallest 7-bit virtual address is just a bunch of zeros, right? 1, 2, 3, 4, 5, 6, 7 zeros. And if we have 8-byte pages, that means like address 0 starts there, and then 8 bytes later is a new page. So address 8, what does that look like? 3, 1, 2, 4, 8. So that's that one. What does address 16 look like? That's going to be 0, 0, 0, 1. Let's see, if that's 8, then 16, sorry, is 1, 0. And then 3 zeros. Then address 24, that would be the next new page. You kind of see the pattern here, would be 0, 0, 1, 1, 0, 0, 0. And so, yeah, you want to be able to reference like offsets. So addresses 0 through 7 are part of one page, addresses 8 through 15 are part of another page. If you think about that long enough, it's these rightmost 3 bits that are telling you where you are in your page. All right, so 8-byte pages, you need 3 bits of an offset for that. So our page offset must be 3 bits. Cool. And with that in mind, we can read the table. So we know that whatever is here, right? This is the offset. This is the virtual address. This is the page number. And this is the offset. All right. So that's going to be just the same in the physical address, 100 for sure. All right. Now our goal is to take this number, this page number. It's page number 0, and we want to offset it and figure out like we want to map it. Right. It's P1 trying to read this address. So we've determined that we're trying to read from page number 0, because it's 4 zeros, and we'll go to that entry of the page table. Okay, entry 0, it is a valid page, and it's in physical memory right now, and it's mapping to frame 3. So we're going to translate 0 to 3, and it's only going to be 3 bits worth of 3, right? So it's going to be 0, 1, 1. The 0 became a 3. That's how you do it. That's how you read it. All right. So I want you to try now. Try for this one. P1 wants to read the 0 address. It's going to map to 6. Right? It's a 7-bit thing, but it needs to map to a 6-bit physical address, right? So map that virtual address to the physical one. See if you can figure it out. So we know that this is the offset, right? It's going to be offset 0, 0, 0, and whatever frame it was. Now we just need to look up. Okay, this was it was page number 0 again, and so it's going to map to frame 3. So again, it's 0, 1, 1. It's at this offset now. Does that make sense? That's how we do it. Okay, so that's the trick. That's the secret. And let's do the rest now. So we know that, let's see, this one's going to be mapped to another 6 bits. As long as it's valid, at least, it's going to be mapped. So this is offset 0, 0, 0. So there that is, 0, 0, 0. Now we just have to map, this is page number what, right? It's page number 2. Is it valid? Yes. So it corresponds to frame number 6. So 6 is 110, and that is going to be the physical address where this virtual address is living in RAM. Okay, that's the idea. So let's do some more. This one again maps to 6-bit physical address, this virtual address. The offset is going to be 0. 0-byte offset, and it's going to be P2 though. P2 is asking for the same address as P1, didn't it? But it's going to be a different place in physical memory because they can't be the same. Okay, so this is P2 going to entry frame 2, right? Sorry, page 2. It's valid. It maps to frame 5. Excuse me. So there we go. So that's going to be 101 for 5, and then offset 0 into that page. And by page, I mean frame. I get it backwards all the time, guys. It's okay if you have to keep looking it up, but these are the ideas. All right, so let's do the rest. There's going to be one that's invalid. We're going to get to that one, and we'll talk about what to do there. You can try the rest though. So okay, we got all these offsets. We know these, right? It's going to be 0, 1, 0 if it is somewhere. So that's going to be 0, 1, 0 for sure. And then we got to map P2's page 1, which is valid, to frame 4. So we're good to go there. Just make it 4. in 3 bits, so it's 100. Cool. And then P2 here, this is the interesting one. It's going to read byte offset 1 from frame, what is this? 8, 9, 10, 11. All right, so we go look up in the P2's page table, page 11. It is not valid right now. If it were, we would put it at frame number 3, but actually that one's in use right now. If you see, like in P1 is using frame number 3. So let's swap them out. Let's make this one invalid. Let's put that one back on the disk, save for later, that page. And then we'll swap out this one for P2, and then now page 11 will actually really map to frame number 3, and we'll be good to go. So we have to go to disk for a second, swap it in. So we go to disk, and then now we're good. Now we're set. We're at offset 001, and page 11 maps to frame 3 now, and it is valid because we read it off the disk. It's in memory now. So there you go. That's how that works. That's how you swap things in and out. Each process gets their own stuff. And then now, let's see, we got P1 trying to read the same offset, the same virtual address. Of course, it'll map to a different physical address. Okay? So it is going to be offset 1, byte 1 again, but the, let's see, but now this 11, right, it's 11 again, but it's the page 11 in P1's page table. It is valid, and it's going to map to frame number 7, okay? And so that will be 111, offset 1 from there, okay? That's kind of how you think about it, and that's what the MMU is doing all day long, and the operating system is also involved to make the page tables, making sure everybody gets their fair share, but that's the secret, all right? And so that's the kind of lookup process that keeps happening. Boop. So just like this. You keep on doing that every time you read an address. But honestly, looking up stuff in a table all day long, that's a lot of offsetting, right? You got to go to some address in a table, offset it, and read the values there. That takes a lot of time, right? So wouldn't it be nice if we could cache that? So we're going somewhere with this. So it takes forever, right? It takes 2 memory accesses for every real address, because one, you got to go to the page table, and then you got to read the stuff there, figure out if it's valid, etc., etc. It takes a while. For every real address, for every virtual address access, you have to go to memory a few times. One to look at the page table, and the one to actually go into memory, right? Into physical memory at that frame you translated it to. So that's disgusting. That's too long. We don't like that. Memory takes forever to read from. So let's cache it. Let's make another cache just for this mapping, just for virtual page to physical frame mappings. Because usually we'll be looking up stuff in the same frame and we'll have it cached. Okay? And the cache is called the TLB, or the Translation Look Aside Buffer. All right? I have a pretty picture on the next slide. We'll get there. Just a sneak peek. But the idea is you go and you look up in the TLB first in your cache for this mapping. You look it up there first, and if it's in there, you're good to go. And you can just immediately go to where you need to go in physical memory, because you know the offset, you know the page, and you're going to get the frame out of this cache. But if it isn't there, if that page is not in the TLB, then you really do need to go to the page table, and then you're going to shove it in the cache in the TLB so that it's there next time, because you're probably going to read from that page again, most likely. Okay, so that's what you do. It's always pages being stored in the TLB map into frames. All right. So here's the secret. It's just a cache. It's just a cache. It's its own little table, but it's hardware table. It's faster. All right. So, for example, let's say you're doing a load instruction. You're doing a load instruction into W0 from X1, something like that. So, all right. Your address is a virtual address. You have you can split it up into a page number and a page offset. And so then you go to the TLB first. On this load instruction, the CPU is going to go look in the TLB. It's a hardware thing. And it's going to go and look for page number P. It's hey, is page number P somewhere in here in the TLB? And if it is, it'll find it. It's yeah, page number P maps to frame number F, and then it can immediately figure out the address and go there in the memory stage of the pipeline. So then it's good to go, right? Maybe this happens in the execution stage, it gets it ready, but you waste no time if it's already in the TLB. Then you just swap out the P with the F, and then you bring on down the D. The frame offset is the same as the page offset. So yeah, if you didn't have the page number mapping to the frame number in the translation look-aside buffer in your TLB, if it was not there in your cache, then you do have to go to memory, sadly. You do need to go to the page table for your current process, and you need to like make sure it's valid, first of all, and then bring in that frame number. You know what it is now, and then you'll put it in there for next time. Because you're probably going to go to that somewhere, at least somewhere in that page again later. All right, so that's the idea, and that's how memory accesses work inside of our running processes these days. We have virtual memory, and we have to worry about mapping virtual addresses to physical frames, virtual addresses to physical addresses, and therefore page numbers to frame numbers all day long. And we try to make it fast with a cache, and we get so much benefit from this. It's really, really worth doing. Now we can't like step on other processes' toes, and if you could even do that, that would lead to security issues anyway. So it's not worth it at all. That's why virtual memory is the greatest thing ever, and now you know a little bit more about it. It is a little complicated, so hopefully as you read the textbook as well, all the gaps will start being filled in your brain. But yeah, as usual, please yell at me if you have any questions about any of this stuff. It's fun to talk about, and I will see you next time.